Boole is concentrating on developing a new type of algebra.
What algebra is, in simple terms, it's the science of putting things together. It's a little bit like playing with Lego. When you take a pile of Lego blocks, there are certain rules you can obey, you have to obey, in order to put the Lego blocks together. The rules whereby you put Lego together, we could call the algebra of Lego blocks.
Boole is trying to develop the rules that we all use when we put thoughts together. These rules will later become the foundation of computer science. To develop his rules, Boole turns to symbols like X and Y. In traditional algebra, X and Y can stand for numbers. Boole believes that the symbols can also stand for thoughts.
Boole was able to develop his algebra of thoughts by realizing that you could have symbols denoting thoughts and you could combine the symbols using algebraic techniques. This indeed was the key idea behind Boole's work.
Just as numbers can be added, multiplied, and subtracted, Boole begins developing a way to combine statements. First, he replaces addition, multiplication, and subtraction with three new operators: or, and, not. Next, he divides all human statements into two types. A statement is either true or it is false. As he combines statements, truth tables emerge. And the tables reveal predictable patterns. For example, when two true statements are combined with and, the concluding statement will always be true. But if a true statement is ever combined with a false statement, the conclusion will always be false. These true-false relationships are at the heart of the modern computer. When a computer runs a program, the program is like a series of true or false statements. The circuits, in essence, correspond to and, or, and not. As the statements enter the circuits, they trigger the circuits to be off or on based on Boole's algebra. For example, when two true statements enter an and circuit, the circuit is open. But when a true statement and a false statement enter an and circuit, the circuit closes. Using Boole's rules, we can orchestrate millions of circuits and write imaginative computer applications. Today, George Boole's algebra is part of all of our lives. That's because computer technology can be found everywhere, in our cars, stereos, televisions, and appliances.
Today we're actually living in a mathematical universe. Most people don't realize they're living in that universe, but whenever they play a CD recording, or they speak into the telephone, or they watch TV, they're getting the results of transmission of information through a mathematical universe.
Bill Massey consults for AT&T, which operates the largest and most sophisticated communication network in the world. A network that relies on mathematics.
all the advances in communications, it allows people to have conversations literally with people across the whole planet. And I think in the future more time has to be spent thinking about how to deal with all this increased information.
In the information age, we certainly are generating a lot of information. There are tens of millions of us hooked up to the internet, creating and sending information. There are hundreds of satellites circling the planet, transmitting information back to Earth. Worldwide, there are 5 billion telephones transmitting voice, video, and other data. To help us manage this invisible web of communication, we rely on mathematics. It's mathematics that also helps make this incredible infrastructure affordable. At AT&T, more than 200 million voice, data, and video calls are routed through the network every day.
NLC, Lucy speaking. How may I help you?
And despite this incredible complexity, the cost to customers like you and me is very low. In fact, as the network grows, costs to us have declined dramatically. For example, a typical 3-minute call coast to coast has dropped an amazing 82% in the last 50 years.
The more interconnectedness that you achieve with individuals, then the more coordination you have to make these interactions work out properly. And so that's where science, technology, and ultimately mathematics becomes very critical.
To help build an efficient and economical system, Massey practices a branch of mathematics called queuing theory.
Well, the word queue is a British English word, and in the United States we would call a queue a waiting line. So in American English, this field would be called waiting line theory.
Queuing theory can be applied to all kinds of waiting lines. Cars wait in line, people wait in lines, production lines, power lines.
Almost any aspect of life where you are sharing some sort of resource with other people, there's going to be some issue of queuing. Sort of how long do you have to wait?
In telecommunications, queuing theory is used to ensure that you don't have to wait long for calls to be connected.